So we're working on this question here after 5 years of this waste lagoon here, is this causing a chloride here? Well, we looked at this using our just advective flow, and we said it would be only 23 meters away, so it's not doing it. But then we're now looking at with the dispersion inside of here. And then we looked at the analytical solution using the Ogata-Banks equation here, where this concentration is the concentration at a specific distance, x, at a specific time thing into there. T is the time since the start of our injection, so that was 5 years ago. Our dl here is our longitudinal coefficient of hydrodynamic dispersion. And our Vx here is our average groundwater flow inside of our system. And so when we look at this, equation, if these are really large, then we can neglect this part of it and we can just look at that. So let's look at this dl here, this dispersion equation, and calculate that first so that we can see where this is coming from. Okay? So if we look at, we're going to look at first that. So if we can look at our diffusion, our LD, or our coefficient of hydrodynamic dispersion. So our dl equals our dispersivity times the velocity times our diffusion equation. So we go 10 meters times 1.4 times 10 to the minus 7 meters per second plus 10 to the minus 9 meters squared per second. And so our dispersivity in the thing is 1.4 times 10 to the minus 6 meters squared per second. These all come from, we said that we're going to go with the 10 meters instead of the 1 meter, because we're going to figure that. We know what the time is. And then we're using a estimation for what diffusion usually is. So we're adding in that diffusivity for a chloride salt. We can look that up. So we would get this dl, and then so what we're going to do is we're going to go back to this equation here, and we're going to assume that this is really large. So we're going to assume that these are really large, and so we're just going to look at this. When we say large, that's kind of hard sometimes to look at inside of here, but you can run them with and without them. Usually we look at this as like, 5 years is long. We're talking like instantaneous right after a short time. So if we do that, we're going to assume that that's all taken care of. We have our concentration over concentration naught equals 1/2 the error coefficient times 100 meters minus 23 meters. This divided by the square root of 1.4 times 10 to the minus 6 meters squared per second times 1.6 times 10 to the 8th seconds inside of here. So the 100 meters is, because when we look at this, is we're looking at the change in the x, so how far away these were 100 meters. And then we're looking at this right here. If you remember that was our analytical, our advection portion of this equation. So this was our advection. So here is our advection portion of it, and it was 23 meters. So our advection says that it's only moving 23 meters after for 100. So that's where those numbers come from. We're going to be looking at 2 over our lateral dispersivity times time. So here's 2 times our 10 to the minus 6. We just calculated that up here. And then our 10 to the 8th seconds is because this is going for 5 years inside of there. And so when we do all of this, you do the square root, and you and all that kind of stuff, and you go in and put it all into your calculator, you'll get the C over C naught equals 1/2, 0.1003. Because what you do is you put this into there, and then you look this number up inside of your error function coefficient thing, the table inside of there, because this number actually works out, this whole thing works out to be 2.57. You look that up, you'll get this. And so when we look at the concentration over concentration naught, we multiply this out, we get 0.00015 for our C over C naught. Well, what does that mean? Well, if our background concentration, our C naught here, is 100,000, so this right here equals that 100,000 milligrams per liter from the well, and then we multiply that 100,000 times this equals 15 milligrams per liter. So it's saying that after 5 years, so what this is saying is this concentration in this well, because, okay, remember, if it's moving by advection, it's just going to be moving as a close front, okay? And then that would say that that has only moved 23 meters. But because of diffusion, because we have dispersion and diffusion, because this is the advection dispersion equation, there's that part that's moving way ahead of it. It's finding the fastest flowing water that it can. It's going to get there. Is that happening within inside of this 5 years? Well, what this is saying is that, yes, a little bit of it is. 15 milligrams per liter of that original 100,000 has reached this well B after 5 years. But the concentration of that well is 100 milligrams per liter. So what this is saying is that according to this, so it's unlikely that the salt from this pond has reached that well. It's just this is probably way under, so the concentration, even if this was flowing into there, 15 milligrams of that might be co-associated with this 100,000, but this is saying that this 100 that's in there is probably a natural source or something like that. And so the beauty of this is, and usually I'm always dealing with long time, so I'm usually getting rid of that, is dealing with this. And so all these different parts you can look up in order to be able to understand if we're going to have dispersion occurring within inside of our system.